And so in just a second or two here, just wanted to make sure that we are, that everyone knows that we are recording. So if you have a problem with with your voice being recorded or whatever, by all means, just don't unmute your mic. But we are being recording. We are recording from this point on. So good afternoon. Airflow and duct design, and specifically, we're going to be breaking this down into modules. And so those modules will be airflow and duct design module 1 and 2 today, and then we'll be doing module number 3 and 4 at a later date. So let's go ahead and pull up our PowerPoint and we'll get started with our airflow and duct design module 1 and 2 today. And Jill, I'll let you kind of be the monitor again to make sure that that you can see the PowerPoint okay.
Yep, everything looks great.
Okay. All right, team. Well, let's go ahead and get started with our airflow and duct design class today. Thank you again for joining us and with training. And as Jill said earlier, please mute your mics. It'll help prevent any echo in the background. However, if you do have a question, please unmute your mic and ask that good question, and we'll address the question for the group as well. So today we're going to be learning about airflow and basic duct design. And some of the subjects we're going to be covering today specifically will be the relationship of velocity and CFM. And then we'll do some practice sessions of CFM based on grill size and velocity. So we're going to ask at this time, either take out a handheld calculator or take your iPhone or your smart device and go to calculator function. Because there's going to be some simple calculations we're going to be doing when we start looking at velocity and CFM. Now, interestingly enough, what happens a lot of times when a technician or when a duct mechanic, they lay out a duct system, they think about CFM, cubic feet per minute, but the key component of velocity or how fast that air is moving across key components in the HVAC system. To give an example, there's a target velocity we're going to be looking at in the main trunk of the ductwork. There's going to be a velocity on all the takeoffs, a target velocity. There's going to be a target velocity across the filters. There's going to be a target velocity across registers and grills. And so, a lot of times we forget about that. We think about just CFM, but we forget that the speed of the air going across those key components is also very critical. So we're going to really dig into that as we talk about velocity and CFM and the relationship of it. So the first burning question I always like to ask with my airflow and duct design class is, what is CFM? Well, as a point of reference, CFM is the amount of air in cubic feet coming out of an opening or moving through a duct section over a period of time, typically 1 minute. So CFM is the amount of air in cubic feet coming out of an opening or a register or moving through a duct system over a period of time, typically 1 minute. And so there's some factors that we have to have before we can determine CFM. So number one, we have to determine the size of the opening or the duct cross section in square feet. Now, team, make a note of this or write this down. You always got to get to square feet. You always have to get to square feet. So what you're going to do to determine square feet, you're going to measure that duct opening or the cross section of that duct. And let's say it's a 10 by 10. I'm just making that up. So that'd be 100 square inches. 10 times 10 is 100 square inches. By 144 to get square feet. So we always have to get to square feet. So we're going to measure that duct, the cross section of that duct or the opening of that duct, and we're going to find it in square inches. Length times width equals square inches. And then we're going to divide by 144 to get square feet. Once we have square feet, we're then going to determine the velocity or the speed of the air, step number 2, that duct in feet per minute. We always have to get to feet per minute. Now, there's a couple tools you're going to need that you can use to find feet per minute or velocity. One of them is what we call a rotating vane anemometer. That little rotating vane tool is that little whizzy wheel guy that you can buy at your supply house there. You go and you buy a rotating vane anemometer. It's just that little whizzy wheel guy. You can blow it and it whizzes around, but that tells you the speed of the air. That's called a velometer or a rotating vane anemometer. That's the big fancy name for it. I like to call it the little whizzy guy. Another type of velocity tool that's very, very common in our industry is what we call a hot wire anemometer. The hot wire is basically a probe. You just drill about a 3/8 hole in the ductwork, in the side of the duct, and you move this probe all the way to the other side of the duct after you drill the hole, and then you move it back towards your opening, and then you read the velocity of the air as the air passes across what we call a hot wire. And that hot wire anemometer is another method of finding the velocity or the speed of the air moving through that duct system or the section of duct that you're testing. So whatever method that you use, we have to find velocity or the speed of the air. And team, you really, if you haven't been doing that, we're going to encourage you to get those tools, either get a rotating vane tool or get a hot wire anemometer so you can start reading the velocity or the speed of the air, because it's a very, very important tool, you know, when you're commissioning a duct system, but also if you really want to know the actual CFM moving through a section of duct, you can use those tools I've just described. So step number 2, we find the velocity of the air moving through the duct or through the opening or through the duct in feet per minute. Then CFM is going to be a simple calculation of square foot opening that we did in step number 1 times feet per minute, or the velocity of the air, and that will tell us our actual CFM. So let's do a couple examples as you kind of take a look at the animation and as you take a look at the PowerPoint. Clear your calculator for me, or your calculator function on your smartphone, and you can check my math here. But let's say we have a duct, a square duct or a rectangular duct, excuse me, that's 18 by 26. So step number 1, we take 18 times 26, and that's going to tell us the square inch area of that duct opening, or the cross section of that duct. So 468 square inches. So 18 times 26 equals 468 square inches. But now hang on a second, we're not done with that. We always have to find square feet. So we take that number and divide by 144 to get square feet. So in our example, an 18 by 26 duct is equal to 468 square inches divided by 144 equals 3.25 square foot opening in this example. Any questions or comments so far? Is everybody good? Okay, well, step number 2, we're going to take our rotating vane tool, or our rotating, either the rotating vane or the hot wire anemometer, and we're going to actually measure the speed of that air coming through that duct section. Now, I realize air doesn't come out in hunks like this. It doesn't come out, you know, in cubic foot hunks. I did that just to make an animation to kind of give everybody an idea that you've got air moving out, and we're going to find it in cubic feet. So in this example, we're going to take 3.25 square foot opening, and we're going to multiply it times, in this example, 60 feet per minute velocity. So we're just kind of illustrating the air's coming out at a certain speed, and that's going to give us 195 CFM. So the actual air moving through that duct section is 195 CFM in this example, because we took the per minute, multiplied those two factors together, and that gave us our, in our example, that gave us our 195 CFM, or cubic feet per minute. So let's do another one real quick. Let's say we keep that same size duct opening, or that same size duct, that 18 by 26, but now we're going to speed the air up to 120 feet per minute. And so same routine, we take the square foot opening times the velocity of the air, in our example, 120 feet per minute, and we see we've increased the CFM to 390. So again, just a kind of a little visual to see what we're doing with measuring actual duct opening times the velocity of the air to get the actual CFM moving through that duct section. And then in our final example, we see we've kept the same size duct, 18 by 26. But in this example, we've moved the air, or we've actually sped the air up to 350 feet per minute. And so that same duct is now. For comments on how we're determining CFM by looking at velocity of the air and the square foot opening of the duct, or the cross section of the duct. So everybody get examples together. We're going to do some interactive examples. So go ahead and take your handheld calculator or your smartphone and clear that calculator function, and let's do some examples together. So the first thing we're going to do, we're going to measure the duct opening, length times width to find square inches. Step number 2, we're going to divide by 144 to find square feet. Now team, you can do this with any duct. I mean, if you ever want to know how many CFM am I actually moving through that duct section, all you have to do is you can calculate the CFM, the actual CFM moving through that duct or that main trunk or through that takeoff very, very quickly. So it's a great tool to have. Again, either a rotating vane anemometer or a hot wire anemometer are great tools to find velocity. So step number 2, we divide by 144 to find square feet. Now in our example here, I'm showing just a little graphic of like a rotating vane tool. But again, you could use a hot wire. You could pull the register off this. In feet per minute, then we'll multiply those factors together, the square foot opening, cross section of the duct, times feet per minute to find actual delivered CFM. So go ahead and clear your calculator for me, and let's do some actual examples together of measuring airflow by using what we call the velocity and square foot method. So in this first example, team, we have a duct opening that's 12 by 30, 12 by 30. So if you'll take your calculator for me, please, and you multiply 12 times 30, that's going to give you, should give you 360 square inches. Once you multiply the duct opening and you multiply the factors together, in our example, 360 square inches, we now so we're going to remember, team, we always have to get to square feet in CFM. So on your calculator, take 360, divide by 144, and that should give you 2.5 square feet. I'll take the velocity of the air in this example. In our example, it's 650 feet per minute velocity. $650 times 2.5 square feet, and that will give us our actual CFM. So go ahead and do that for me on your calculator. Multiply 650 feet per minute velocity times 2.5 square foot opening of the duct. And then the actual CFM should be 1625. So that duct right there, let's say this is the main trunk on a unit, and let's say it's a 4-ton unit. That would be sufficient for a 4-ton unit, that size duct, 1625 CFM. Now at this time, I'd like everybody please to write this down or to please make a note. We always want to size our main trunk. We always want to size our main trunk. We always want to size our ductwork, our entire duct system. We want to size it to deliver 400 CFM per ton of cooling. So if I've got a 2-ton unit sitting outside, I'm going to need to design my ductwork to deliver 800 CFM, total CFM into that space. Deliver 1625 CFM in our example. So that ductwork that we've designed right there should be fine for a 4-ton unit. We always want to design our ductwork ductwork. We always want to design our ductwork for 400 CFM per ton of cooling. 400 CFM per ton of cooling. So again, if I've got a 3-ton unit setting outside, I need to design my ductwork inside the space to handle 1200 CFM at 400 CFM per ton. Any questions or comments so far? Go ahead and unmute your mic if you have any questions.
What was the original duct size we were using on this one?
Let me back up.
So
Good question.
I just typed it.
A 12 by 30. So a 12 by 30 is going to give us a 2.5 square feet. And if we have designed our main trunk velocity at 650, and actually we'll cover that in a little bit. The target velocity on your main trunk should be around 700. So this is actually going to be pretty close to what you'd have on a properly designed duct system. So, we said 700 to 900 is what Manual D recommends. So 650 is pretty close. So this 12 by 30 would be sufficient for a 4-ton unit based on that velocity requirement. Good question. Any other good questions or comments? Okay. Well, let's go ahead and do a few more examples together. In the second example, it's a take 14. Now remember, team, we always have to get to square foot. So we're gonna take that 308 and we're gonna divide by 144 to get square foot opening or square foot cross section of that ductwork or that section of duct. Now, team, remember this will work on your main trunk. It'll work on your takeoffs. It'll work on if you've got a rotating vane tool, you can use it at registers. You can use it at return grills. And so it's a very, very versatile tool, that rotating vane tool. So if I take 308 and divide by 144, that's going to give me a 2.1 square foot opening. 2.1. And in this example, we have a velocity of the air is 745 feet per minute. 745. So we then take that 745 and multiply it times the square foot opening, or the cross section of that duct, 2.1 in this example. And so in this second example of measuring airflow using the velocity method, the actual CFM moving through this duct is 1565. So we have a 2.1 square feet times a 745 feet per minute. So team, that's an important concept. We can always find airflow by looking at the cross section of the duct, measuring the cross section of the duct, and then find the speed of the air in feet per minute, and we can find CFM moving through that section of duct. Any questions or comments? Okay. A couple more examples. We'll do 1 or 2 round examples here in a minute, but let's do one more square example or rectangle example just to make sure everybody's got this in your head. So in this rectangular example, we've got a 10 by 16. 10 by 16. So clear your calculator and take 10 times 16. That should give you 160 square inches. We then divide 160 by 144 to find the square foot cross section of that duct. In our example, it's 1.1 square feet. We then measure the velocity of the air. In our example, it's 825 in this example. So we take 825 velocity in feet per minute times 1.1 square feet cross section of the duct, and the CFM we're moving in this example is 908. So that 10 by 16 at 825 feet per minute velocity is moving about 900, a little over 900 CFM. So this is a quick, easy way, again, to determine and to commit setting up and checking airflow in a particular section of duct or in the main trunk if you have access or get access to the main trunk and find your airflow. Any questions or comments on rectangular duct before we try a couple examples? Okay. Well, when we're looking at round duct, there's a little formula we're going to have to look at. And so if you remember back in about the 3rd or 4th grade, you know, when you're learning basic geometry, the radius of a circle is called, the radius of the circle is 1/2 the diameter. So if you take the distance across the circle and divide it in half, we call that radius. And so if you remember that little formula for finding the area of a circle, we're going to apply that to round duct. So in our example, we're going to take the radius times itself, whatever 1/2 the diameter of that duct is, will be the radius. Take the radius times itself, times that mathematical constant of 3.14. Now, team, I realize that 3.14 goes on indefinitely, so we've just rounded it off 2 digits for field purposes. That's plenty close enough for doing ductwork. That number, that 3.14 number, is a mathematical constant that actually goes on into infinity, and it never repeats itself. It's actually a Greek thing called pi. And so, but 3.14 is plenty close enough for field work. So it's radius times itself times 3.14 equals the square area of that circle or that round duct. Once we have that information, once we've got the square area, we can divide by 144, just like we did before, to find square foot, and then take the velocity and find the velocity of that air and the CFM coming through that round duct section. So, but we have to apply just a little bit of math for that round duct. So in this first example, let's go ahead and do this together. We have a duct opening that is 16-inch diameter, 16-inch diameter. So we're going to take 1/2 of 16 to find the radius, and in this example, that would be 8. 8 inches would be 1/2 the. Take 8 on your calculator. Take 8 times 8 times 3.14, and that's going to give us the square area of that round duct, and that should be around 201 square inches. So 16-inch diameter, we divide that in half to find the radius, which is 8 inches. We then take 8 times 8 times 3.4 to get to square feet. To get square feet. And we find that the actual square foot cross section of that 16-inch duct is 1.40 square feet. Any questions or comments on how we derived that number? We'll do a couple more examples, but we want to make sure everybody knows how we got there first. Everybody good? All right, so we take 1.4 square foot of that 16-inch round duct. We find the velocity of the air just like we did before. So in this example, we have a velocity of 725 feet per minute. We then multiply 725 feet per minute times the square foot cross section of that 16-inch duct, which happens to be 1.40 square feet. And the actual CFM we're moving through that 16-inch round duct is so based on Manual D and based on recommended velocity standards set forth in Manual D, residential duct design, at 725 feet per minute velocity, that 16-inch round duct would be good for a 2.5 ton unit in this example. Now that's presuming that that velocity is an acceptable velocity, which it is, because Manual D recommends 700 feet a minute of velocity in a main trunk. So if this was the main trunk on a unit, 16-inch round duct, it'd be good for a 2.5 ton unit at 400 CFM per ton. Any questions or comments so far? Okay, team, well, let's do a couple more round examples just to make sure everybody's got this, then we'll jump into something else. So in this second example, the second round duct example, we have a duct opening that's 14 inches. So the first thing we have to do is find the radius of 14 inches. So divide 14 by 2, or 1/2 the diameter of 14. And that gives us 7 inches. So on your calculator, take 7 times 7 times 3.14. That should give us a opening, a square inch opening of 154. But now hang on a second, we always have to get to square feet. So we divide 154 by 144 to get a square foot opening of this 14-inch of 1.07 square feet. Once we find the square foot opening of that duct, we then measure the velocity of the air stream. And in our example, it's 810 feet per minute velocity. We then multiply 810 times the square foot opening of 1.07 in our example. And then that gives us a CFM of 867. So in this example, if we can live with 810 feet per minute velocity in that section of trunk, or in that section of duct, and we'll look at that. We'll look at more of that later on when we start looking at some of our Manual D tables. 810 feet per minute velocity times 1.07 square feet, that gives us 867 CFM. So that'd be good for about a 2-ton unit. So that 14-inch round pipe, or that 14-inch hard metal pipe, round insulated, would be good for about 867 CFM. Any questions or comments? Okay, team, well, let's do one more and then we'll jump into something else. In this final example, we have a duct opening, or we have a 22-inch diameter duct, 22-inch diameter. So the radius is going to be 11 inches. So clear your calculator for me and take 11 times 11 times 3.14. And that'll give us the square inch opening of this round 22-inch duct. In this example, it's 380 square inches. But now hang on, we got to always convert to square feet. So we take 380 and divide by 144 to get a square foot opening of 2.64 square feet. We then measure the velocity of the air either with a rotating vane tool or a hot wire anemometer, where we can just poke a hole in the side of the duct and take that hot wire and go in the duct and read the velocity of the air. In this example, it's 760 feet per minute. We then multiply 760 feet per minute, the velocity of the air, times 2.64 square feet. And in our example, the CFM would then be 2006. So this 22-inch round duct, let's say it was the main trunk on a 5-ton unit, that would be sufficient for a 5-ton unit based on 400 cooling and based on a design velocity of 760 in our example for velocity. If that's an acceptable velocity on a main trunk, which it is, and we'll look at those tables a little bit later on, that would be sufficient for a 5-ton unit. 22-inch round, metal pipe, insulated on the outside, would be a good duct size for a 5-ton unit. Any questions or comments on looking at the cross section of a duct, measuring the velocity, and determining the CFM on that duct section? Any questions or comments on that before we move on? Is everybody good? And just to make sure, Jill, can you still hear me okay? Everything streaming okay?
Yep, I can hear you and we're good.
Okay, sounds good. Okay, so the next thing we're going to talk about, team, is free area of grills and registers. Because we know from a practical standpoint, you're not going to just have a duct opening blowing air into a space. Now you might in a garage or a closet or something like that, but it's just not practical to not have some sort of a register or grill in front of that duct opening. But see, as soon as we put a grill or a register in front of that duct, we're going to change the characteristics of the air coming through that register or grill. And so we have to account for that. And so typically most grills and registers are going to be about 80% efficient, something like that. So, I mean, you can have wooden grills that are horribly inefficient that might only be flowing 30% of the air behind it. And you may have some really high dollar specialty grills that, might have a 95% efficiency. But if from a design standpoint, if you'll figure that your grill or your registers are going to be somewhere between about 80 to 85% efficient, that's a good spot to be from a design standpoint. So you have to figure, when you're looking at grills and registers, you have to kind of figure in, or you have to take into account all the slats and the cross sections of all those pieces of material that are hanging out in the airstream, so to speak. So to do that, what we're going to do, we're going to measure the grill or the register opening where air can actually move through the opening, and we're going to convert to square inches and then to square feet, just like we did before. But we're going to add a little bit of a multiplier in there to account for that 80% efficiency. We find the square foot area, we're going to multiply times 0.8, which is the same way of saying, well, gee, the cross section is really about 80% of the efficiency of the actual opening where that air can move through, to obtain what we call free area, free, F-R-E-E, free area. So if you'll figure registers and grills are about 80% free area, that'll keep you out of trouble when you're designing a duct system. As I said, grills and registers can range anywhere from 25 or 30% efficiency all the way up to about 95% efficiency, but a good solid field number for just a standard grill or register is about 80%. And so you'll measure the register or grill where air is actually moving through, and this works fine for return grills or supply registers, either one. Just measure the area where the air is coming through and convert to square feet, multiply by 0.8 to find free area, and then take your velocity ratings and do just like we did before. But let's do a couple examples of looking at the free area and airflow across grills and registers. So in our example, we have a 20 by 30 grill, and we'll just say it's a return grill. And so that's 600 square inches, right? Now remember, we're going to add that multiplier of 0.8 to find 80% of that. So we'll take 20 times 30. And then we'll divide by 144 to get square feet. And then we'll multiply times 0.8 to get an actual free area in our example of 3.3 square feet. So just as a quick little exercise. So if you have a 20 by 30 grill, you take 20 times 30, divide by 144 to get the square foot area, and then multiply that number times 0.8 to account for that 80% efficiency of most grills and registers to get an actual free area of 3.3 in our example. Is there any questions or comments on that as we do a couple grill and register airflow checks? Any questions or comments on that? Okay, well, let's do a couple examples then, team. Go ahead and clear your calculator for me. This is called the velocity method for It's the velocity method of measuring airflow across the grill or register. And so step number one, we're going to measure the grill and convert to square inches and then multiply by 80% after we get square feet to find free area. So in our first example, we have a 24 by 30. We have a 24 by 30 grill. Let's say it's a return grill. And that gives us 720 square inches. So 24 times 30 equals 720. We then divide by 144 to get square feet, and then multiply that number times 0.8 to get free area. So in our example, we've got a grill that's 24 by 30. We then divide by 144. It gives us 5 square feet. But then we're going to figure the free area by multiplying times 0.8 to get free area. So in our example, we have a 4 square foot free area on that grill. Now, once we have that free area, team, what we're going to do, we're going to divide that grill up into 4 to 12 equal test areas. Let's say this is a return grill, and we want to know how much air is going across this return. And so divide that grill up into 4 to 12 equal test areas. Now, this is really important. Team, you don't have to take a chalk line or a ruler or anything like that. Just visually, just visually kind of divide that grill up just visually so you have, 4 to 12 equal test areas. So in our example, we've got 6 test areas. We've divided this grill up, and we're just doing it visually, and we've got 6 test areas in our example. And then what we're going to do, we're going to measure the velocity of the grill in those test areas, and then add those velocities up and divide by 6 in this example to get an average velocity. So clear your calculator for me, and we're going to find the average velocity across this grill or register by taking multiple readings. So clear your calculator. The very first reading we have across this grill in this example is 325 feet per minute. So what you're going to do on your calculator, you're just going to keep adding the numbers until we get to the end, and then you'll divide by the number of readings in our example 6. So we're going to take 6 readings and add them up, and then divide by 6 to get an average velocity. So clear your calculator. Our first reading is 325 plus 355 is our second reading, plus 402, plus 395, plus 325, plus 485. So as we take all those readings together, we add them up, and whatever that number is, you divide by 6 to get an average velocity. So in our example, our average velocity is 381.2. And you can drop the 0.2 if you want to. That's just how it worked out on the calculator. So 381 is the average velocity across that grill in this example. So we're going to take that average velocity and go back and multiply it times the square foot area. In this example, it's the square foot free grill is 4.0 square feet. And then that'll tell us the CFM we're actually moving across that grill or register. And so using the velocity tool, the rotating vane velocity tool, is a quick, fast, easy way to measure air going across the return grill. Now I'm going to caution everybody, or I'm going to ask you to do a couple things. If this is a return grill with a filter in it, take the filter out and do all your readings and mark it down. In our example, it's 1525. And then put the filter back in and do it again to see how much loss you're going to have going across the filter. And it'll shock you sometimes, especially like these pleated filters that homeowners stick in their return grill. It'll shock you how much airflow loss that you have with that pleated filter in there. So we highly recommend that, you know, if the homeowner's using pleated filters, that you're going to add some returns in the home, because pleated filters are extremely restrictive, and it'll shock you the amount of CFM, you know, they kind of eat up, so to speak. So if you've got a return grill with a filter in it, take the filter out and do your test and find the CFM, and then put the filter back in and then do it again. So this is just a real quick way to commission a return system if this happens to be a return grill, and it'll give you a good idea what's going through the system. Because remember, team, the fan inside your indoor unit can only blow what it can suck through the return. So give you a good idea what's moving through the system. Let's do another one real quick, and then we'll get into something else. So in this second example, clear your calculator for me, please. We have a 30 by 30 grill. And if we take 30 times 30, that's going to give us 900 square inches. We then divide by 144 to get square feet. And then multiply that number times 0.8 to get free area, free area. So 30 by 30 grill, 900 square inches, divide by 144 gives us 6.25 square feet, times 0.8 to find free area. In our example, that 30 by 30 grill is a square foot free area opening of 5 square feet in our example. Then you go ahead and clear your calculator for me, and we're going to take velocity readings across that grill. And then we're going to average them together. So your first reading, so clear your calculator, your first reading is 320 plus 330 plus 320 3. So if we add together and divide by the number of readings, in our example, we took 6 readings. So you take all those numbers and add them together and divide by 6. That gives us an average velocity across that grill or register of 325. Once I have my average velocity across that grill or register, I then multiply it times the square foot free opening, in our example, 5 square feet, and that gives us a CFM of 1625. So if I had so let's say I've got a 4-ton unit and a single here in Alabama. I know up north we have multiple returns in homes, but a lot of times down here in Alabama in the South, we'll just have one big return grill for the whole house, sitting in a hallway. And so in this example, that 30 by 30 grill would probably be something you'd find on a 4-ton unit if you had just a single return. So this free area and velocity, finding CFM and free area across a grill or register and cross section of a duct is a very important way to measure airflow. We're going to talk about more than one way to measure airflow before this course is over, but this is called the velocity method, the velocity and square foot method of measuring airflow. You can do it across grills or registers. You can also do it, as we learned a minute ago, looking at the cross section of a duct as well. Any questions or comments on using velocity and square foot area to find CFM in a duct system? Any questions or comments? Everybody good? Okay. Well, let's go ahead and jump into our next module then. We've been trying to do 2 modules when we do our training. That's worked out really, really well to do, you know, module 1 and module 2 as we break our units down into, not our units, but our training down into modules. So any questions or comments on using the velocity method or finding the area of a grill and finding CFM moving across the grill or register before we jump into module number 2. Okay, well, welcome to module number 2 today. Today we're going to be, again, learning some basic airflow and duct design principles, if you will. And so we're going to review the duct calculator in this particular portion of the program. We're going to actually review the duct calculator. And we're going to be taking a look at required CFM for different size units, as well as talking some about return and supply duct sizing based on Manual D recommendations. So in this portion of the program, we're going to be looking at an air duct calculator. And the air duct calculator that I'm featuring is just a real simple one. It's a round one. As we take a look at that air duct calculator, we're going to be talking about some different components on that air duct calculator. Now, just a real quick question: does everybody have air duct calculators at their station or are available to them? So as we talk about an air duct calculator, you'll be able to follow along and look at the key components on this duct calculator. So does everybody have a duct calculator today?
Yep.
Okay, well, fantastic. All right, so as we take a look at the air duct calculator team, one of the first areas we're going to look at is you're going to find on your air duct calculator, there's going to be a window, and there's going to be as you turn this air duct calculator, or if you have one that pulls in and out or slides in and out, you're going to be able to find velocity in feet per minute at any given CFM. So on that air duct calculator, you're going to be able to line up velocity and required airflow in those windows. And once you do that, it'll start giving you information, in different parts of the calculator as far as duct sizing and equivalent sizes for rectangular duct. And there's all kinds of stuff, but these duct calculators are designed to give us important information when we're designing a duct system. And the first window I always like to talk about is velocity in feet per minute and at any given CFM, because that kind of goes hand in hand on what we talked about earlier in module 1, that there's always going to be a velocity and a CFM relationship. Once we know what velocity that we're designing to, and we know the amount of CFM that we're designing to, and we line those up in the duct calculator, we then can come over and find out what size duct is going to provide that. And so the second component on the air duct calculator I'd like everyone to make note of is the round metal duct diameter size to do that. So if you take a look at that air duct calculator, let's say, for instance, in our example, we lined up, just looking at the PowerPoint, to make it simple, we lined up 1,000 CFM at 1,000 feet a minute velocity, in our example where they kind of line up 1M and 1M lines up there. So we find out that if we have 1,000 CFM at 1,000 foot a minute velocity, which is pretty fast, that would require about a 13-inch duct, something like that. And likewise, that same duct, if you take a look at the air duct calculator in that first little window we talked about, 500 feet a minute velocity and 500 CFM takes the same size duct. So the point is based on velocity and based on the amount of air you're wanting to move, it's going to tell you, the duct calculator will tell you what size round duct that's going to take to do that. And you can also see that that same duct, at different velocities is going to provide different CFMs, based on what you're designing to. So any questions or comments on that so far? Once we know the velocity that we're designing to and the amount of CFM we need, we can look in the window where it says round duct size, and we can determine what size duct we would need to have that velocity and that CFM delivered. The third component, and we're going to see that maybe we've got a construction constraint, or maybe we're not using round duct, but maybe we're using rectangular duct. And so the third component on the duct calculator we're going to talk about is a rectangular equivalent to round duct dimensions. So in other words, if I in this example, if I've got like a 13-inch round duct in our example on the PowerPoint, we see that an equivalent rectangular duct might be something like a 10 by 14, or maybe a 15 by 11, and so on. You guys can kind of see where I'm looking at on the bottom of the duct calculator. So where those lines line up together, you can find that you've got a different size duct. Rectangular duct will give you the equivalent airflow of a round duct. So that's the third component on the air duct calculator, is we can always find a rectangular equivalent. So in our example, again, we've got about a 13-inch round duct in the round duct window. And down below, it looks like we've got about a 14 by 13 for those numbers down there would give you an equivalent airflow. Now remember, this is equivalent airflow, not the amount of sheet metal used to actually make that duct. So it's important that we understand that this rectangular equivalent dimension has to do with equivalent airflow. Look at the top of the duct calculator in this example. We have friction loss at the very top, and that friction loss is going to be given at any given CFM. So in our example, let's say we're looking at 500 CFM. So let's just kind of walk through this. So the first thing we talked about was velocity and CFM. So let's say we line that up. In our example, if you take a look at that window on the right, the velocity in feet per minute and the air volume in cubic feet, we see that we have 500 and 500 lined up together as an example. So at 500 CFM, at 500 feet a minute velocity, we need about a 13-inch round duct, or a rectangular equivalent of about a 13 by 11, something like that. And then if we look at the very top of the duct calculator, the friction loss, we find that at 500 CFM, with that size duct, 500 CFM, it looks like we're going to have a friction loss of about let's see, a 0.2, 0.03, about a 0.04 inches of water column. This is all in inches of water column, the friction loss per 100 feet of duct. So if I took 100 feet of that duct and put a fan on the end of it, and I was blowing 500 CFM through it, and we measured the static pressure loss on that fan, we'd see that it would be about a 0.035 to 0.040 inches of water column external static pressure. Okay, and so when we look at friction loss, we have to remember this is per each 100 feet of that duct. So the air duct calculator gives us we can design a duct around a particular size duct at any given velocity or CFM, and it'll tell you our duct size. It'll also tell us the amount of friction loss per 100 feet of that selected duct. So any questions or comments on the basic function and the information that's being provided on the air duct calculator? Let me go ahead and ask everybody to unmute their mic if you have any questions on the air duct calculator. Everybody good? Okay, so we're going to be using these. You're going to be using some of these functions when we actually get into designing a duct system in some of our further modules. We'll be using the air duct calculator to actually design a duct system a little bit later on in our program in our later modules. Okay, so let's talk a little bit about some recommended duct velocities based on Manual D. Now this is Manual D. This is right out of Manual D. And this is important, team, because a lot of times what happens is when a technician or a duct mechanic, they lay out a duct system, they don't take into consideration the velocity of the air moving through those sections of duct. So it's very to these recommended velocities, we're going to have a system that's going to be noisy and inefficient. Because remember, team, it's the speed of the air that's going through the duct system that people hear. It's not the volume of air, so to speak. It's how fast the air is moving is really what they're hearing, the velocity. In addition, getting into manual D, if manual D, or go online and look through a manual D. Manual D, the ACA manual D, is the criteria set forth in our industry for airflow and duct design residential systems. And so as we take a look at ACA manual D, we find out that a very, very important thing that sometimes we often overlook is the velocity of the air across those system components. You'll find if you dig deep enough in manual D, you'll find that cooling coils, like evaporator coils on an air conditioning system, have a recommended velocity across that coil for it to work properly. The heat exchangers on a furnace are designed to have a given velocity of air going across them, and so on. And so as we start designing our duct system, we need to take into consideration the velocity of the air that we're designing to as we move air through that duct system. We want the system to be quiet. We want it to be efficient. We want to make sure we have sufficient air coming out of the registers to throw that air out into the conditioned space. But we also don't want it to be noisy, and we want to make sure that our system components, like evaporators on the air conditioners and the indoor coil on a heat pump and the heat exchanger on furnaces and so on, are working at their optimal velocity across those coils and across those heat exchangers based on manual D. So when we design a duct system, we really want to focus a lot on velocity and to make sure we're with a little bit of that. So these are recommended. And this is our main trunk, our main supply trunk. The maximum is 900. Now remember, team, that maximum, you probably want to avoid that when you design, only because, to stay, towards the lower end of our 725 velocity on the main trunk, and avoid those higher numbers so I have a nice, quiet, efficient system. On the return side, the return, if you have like a main return coming back, you want to keep that velocity coming back to 600 or less. Maximum is 700. Recommended is around 600 velocity on the return trunk. That's the actual big main return trunk coming back. If you have multiple returns and you have a return trunk, on your branch ducts, you'll minute velocity on your supply is recommended, and 400 on the return is recommended. Now, team, one of the things I'm going to supply takeoffs, put a manual damper on there that you can access so that you can balance the airflow when you're done. So once you design a duct system, you're always going to want to go back and balance that airflow. And a good way to do it is to have a manual damper on each. That way you can balance the airflow very, very nicely into each conditioned space. As you condition that space and you commission the duct system, you can actually put the recommended CFM into each space, based on your airflow requirement. So on your branch ducts, we recommend a damper on each takeoff so that you can balance your airflow. Now on registers and grills, you're going to notice they're the same. Registers and grills we're going to recommend 500 feet a minute is what manual D recommends on the supply, and 400 feet a minute velocity on the return. And you'll notice that the registers are 500 feet a minute. They're a little bit less than the branch duct, and that's because we want to keep it quiet. Now, some local codes, for instance, down here in Alabama, because we have a lot of heat pumps down here, we have a local code that supersedes manual D, and the local code says they want 550 feet per minute on a register. And the reason they want that is they want a little bit more throw on the register on heat pumps so that they get a better circulation in the air. But if you, unless you have a local requirement that supersedes Manual D, we recommend you always design your duct systems with these factors in mind, because again, Manual D is kind of the, it isn't kind of it, it is the standard with which we design our duct systems, in the industry. So registers and grills and diffusers, 500 feet a minute is recommended on the supply, and 400 on the return for those components. Any questions or comments so far? Okay, now the final one on here that I want everyone to really, really pay attention to is our filter grill. So if you've got a return grill that's if you've got a return grill that does not have a filter in it, keep that velocity, you can have that, 400, 450 feet a minute velocity, you'll be okay. However, please watch this. Please note this. The maximum recommended velocity across a grill with a filter in it is 300 feet a minute. So we drastically oversize, or not really drastically, but we want to make sure that if you've got a return grill, if you've got a filter grill with a filter in it, make sure you set that return grill up, or you design that return grill to not exceed 300 feet a minute velocity across that return. And the reason that is because the recommended Manual D velocity across a filter is 300 feet a minute. Because just think about it, team, anytime you have particulates moving across a filter, a return air filter, you want to capture those particulates. You don't want the air moving too fast, because it can drive those particulates through the filter. And so based on the type of filter you have, this becomes very, very important for optimal or maximum filtration. So please do not exceed 300 feet a minute velocity if you have a filter in your return grill. If you don't have a filter in the return grill, 400 to 600 feet a minute velocity is the recommended on the return. And I like to stay more towards the 400. That gives you a nice quiet system. Oh, and by the way, if you go to a homeowner's house, excuse me, it's easy at the return grill. I can promise that return grill is undersized. So a properly sized return grill should not be noisy, and especially if it's a filter grill, it should have a nice low velocity across there. 300 feet a minute velocity is the maximum recommended according to Manual D. Any questions on recommended velocities, excuse me, set forth by Manual D? Okay, team, I'll tell you what. Well, that concludes our module number 1 and 2 for our airflow and duct design. I'm going to ask everyone before we do module 3 and 4 next week to really get familiar with your air duct calculator, because next week when we pick up our module number 3 and 4, we're going to be building a duct system, and you're going to want to be proficient with your duct calculator. And we'll cover those components next week. But any questions or comments before we conclude for the day on our module number 1 and 2, airflow and duct design for everyone? Any questions or comments?
Joel, I'd like to thank everyone for participating. In the next few minutes, I will be sending them all the post-test from today's session. So
okay.
They can take that test and email it back to me. I'll be happy to score it for them and send it back so they know how they did. And then if there's any additional information that they're needing for next week, they can reach back out to me through my email.
Jill, that sounds real good. And I'd like to tag onto that as well. Thank you so much for your attendance today and taking the opportunity to train with us today. We do appreciate it. And what we'll be doing here after we conclude our training, we'll have this recorded session. We are recording the session, and we'll get that loaded up onto our Champion and Wind Supply training YouTube channel here in the next day or so, or possibly this afternoon yet. And so able to review what we've done today in this session. And today's session will be called Airflow and Duct Design, Module 1 and 2, Session 10, or whatever the date is today. So let's see, the date is, so it'll be 10/13/2020 is the day's session. So you can go out and review what we've done today on the training site once I get that loaded up. But thank you for your attendance today. Any other final questions or comments, Joe, before we shove off today?
That's all I've got. Have a great rest of your day.
Thank you. You too. Have a good day, everyone.